Section 2.5 Physical Applications. For this problem, we have Newton's law of gravity, and the force equals G times mn over r squared, where r is the distance between the bodies and g is a gravitational constant. If one of the body is fixed, and find the work needed to move the other from r equals a to r equals b, and your answer should contain g, mn, r, a, and b. And in fact, r is gone when we do the integration. Okay, so how do we solve this problem? Well, we use the formula, right? The work equals force times the distance. We have to do an integration because the force is changing based on distance. If you take a look at the formula for F, when R changes, F changes. So right here, that's why we need to use integral. So to set it up is just integral from A to B, F, G, M, N, divided by r squared dr. And the reason we set it up this way is because r really represents the distance. Okay, so dr is also telling us how the distance is changing. And the force is also changing according to the distance. And r is from A to B. Now, how to solve this integral? We treat everything not r as a constant. The only thing that is changing is r. Okay, dr means r is changing. D means delta, changes. So we factor out everything that's not changing, which is g, m, n, integral from a to b, 1 over r squared dr. You can think of it as 1 over x squared dx. And we do know the antiderivative. The antiderivative of 1 over r squared is negative 1 over r. Okay, you can look up the integration table or recall the general power rule. And now r is from A to r equals b. Okay, so you plug that in. So you will get g m n negative 1 over b minus negative 1 over a. You can leave it like this, so you can just write down as g mn 1 over a minus 1 over b. Or any equivalent form should give you the point.